How are you? The sun is too hot here in Hyderabad nowadays.
Subrata, would you like to share your screen once? Are you able to hear me? Subrata, are you able to hear me? Hello? Can you hear me?
Can you hear me?
না আমি শুনতে পাচ্ছি না no I cannot hear you Jyotirmoy
Can everyone else hear me?
Yes, I can. I can hear. What can you? Your audio is off.
oh acha
I think it's muted.
Jyotirmoy, can you hear me?
Yes, I can hear you. I can hear you.
Okay, fine.
Can
Thank
you please share your screen?
Okay.
Yeah. That's
that all
fine.
right?
Can
Okay.
you please put it to the presentation mode as well?
Okay. Slideshow. Slideshow.
Yeah,
Is that
perfect.
all? Okay.
Perfect.
Fine,
Can you please move a few slides up and down so that we are fine as well? Yeah, looks good.
Thank you.
All right. So we'll start in next 3-4 minutes. Let some more people join.
Yes. Give your green signal. I'll start immediately. নমস্কার স্যার জেঠি স্যার নমস্কার
Namaskar. Subrata.
থ্যাংক ইউ স্যার
think the speaker by mistake left the meeting somehow. I hope he will. Okay, he's back. Would you like to present once again? I think you left the call by mistake.
Can you see the screen now?
No, we can't see the screen. You need to share it once more.
Okay.
Good morning, everyone.
Good morning. Good morning.
Good afternoon.
Good morning. আমাদের এখান থেকে গুড আফটারনুন নেচুন্দা থ্যাংক ইউ
Okay.
হ্যাঁ স্যার প্রফেসর মুখোপাধ্যায় দিলীপ মুখোপাধ্যায় নমস্কার হ্যাঁ
প্রেজেন্টেশনটা অন হচ্ছে, মুখটা দেখা যাচ্ছে।
Mute myself.
কোচ Jyotirmoy, can you see it now?
Yes, please put it in the slideshow mode.
Yes. Okay.
Okay, I think we are 3 minutes past 4 and let others join. Meanwhile, let's just start the meeting. So, good afternoon, everyone. Thank you very much for joining this month's e-seminar. And I am very glad to announce that we have Mr. Subrata Ghosh today delivering a talk on the big picture of the tectonic-geodynamic evolution of the Himalayas. Mr. Ghosh is currently an associate professor and head of the department in the Department of Geology of Dibrugarh Government College, West Bengal. His transferable service in the WBES cadre allowed him to acquire valuable experience in UG, PG, teaching in geology as well as in higher education administration. He had served as the registrar of the Rabindra Bharati University, Kolkata, and as the member secretary of the West Bengal State Council of Higher Education. Coming from a remote village of Murshidabad, district West Bengal, Mr. Ghosh chose to study geology in Presidency College, and then he stood first in BSc Honors as well as, and then later on also did his MSc from the same university. After his master's, he went to University of Edinburgh to do further studies, where he was also awarded with the prestigious ORS award, and he actually owes his journey to some of the very renowned teachers in the field of structural geology, Professor Dhruva Mukhopadhyay, then Professor Tapos Bhattacharya, Professor Dilip Shaha, Professor Shubho Shankar Sarkar, to name a few. So with this brief introduction, may I now invite Mr. Ghosh to deliver his talk. Over to you, sir.
Thank you, Jyotirmoy, and a very good afternoon to everyone present. My topic is on the big picture of the tectonic geodynamic evolution of the Himalayas. We know for a long time there are several controversial issues in Himalayan geology. Although the researches in Himalayan geology have been continuing for nearly 2 centuries, these long-existing controversies were not resolved. So through this talk, through this talk, I will try to resolve some of those controversies, as well as I will try to reveal some important aspects of the tectonic geodynamic evolution of the mountain belt. And at one point, I would try to highlight the importance or requirement of systematic geophysical studies along a few transects across the Himalayas for comprehensive understanding of the tectonics and geodynamics and the evolutionary aspects of that in the Himalayas. I structured the talk in this manner. There are 4 sections: setting the context, then resolution of several nagging controversies in Himalayan geology, the newly revealed aspects of Himalayan tectonic geodynamic evolution, requirement of the confirmatory geophysical investigations, and finally, conclusions. Setting the context. In 1987, after going to Edinburgh for doing my post-MSc studies, I was privileged to attend a very famous group discussion at the Royal Society of London, and it was titled Tectonic Evolution of the Himalayas and Tibet. I was very thrilled, and in fact, I asked several questions, and at that time, many of the important or world-famous geoscientists working in the Himalayas, they attended that conference. So it was a great revelation for me. In the general discussion, I put forward one question, then how to solve many important burning issues in Himalayan geology. What are those issues principally? Professor Phil England from Oxford University, he, on behalf of the dignitaries, replied, and that was also printed in that edition. And he mainly highlighted that international collaboration, among all other things, is also going to be very important. And that's very true. Many people cannot go to the place they want in Himalayas even today due to many practical problems. The Himalayas and its neighborhood. We know the Himalayas and Tibetan Plateau, these are the widest zone on the earth with the highest altitude. This brown colored area here to the north of the Indian Peninsular Belt. On the right hand side, the black box shows the location of the Himalayas. The Himalayas is the tallest part in the southern portion of that Tibetan Plateau Himalayan range. The Himalayan domains, the Himalayas have distinct domains, principally 4 domains. Starting from the south to north, they are Sub-Himalaya or Shivalik Himalaya, Lesser Himalaya, Higher Himalaya, and then the Tethian Himalaya. Beyond the Tethian Himalaya, we get what is called Trans-Himalaya. Now, all these Himalayan domains are bounded by important tectonic boundaries. The northernmost, that is Tethian Himalayan domain, is bounded to the north by the ITS, Indus-Sangpo Suture, and beyond that is the Trans-Himalayan belt. Trans-Himalaya is not included in the, traditionally speaking, in the Himalayan zone. The Himalayan zone has 4 divisions from north to south: Tethian Himalaya, Higher Himalayas or crystalline Himalaya, Lesser Himalaya, then the Shivalik Himalaya. Okay, and Shivalik Himalaya is bounded to the south by the main frontal thrust. And beyond that, to the south are the Indo-Gangetic alluvial plains of North India. On a satellite image, we can show the different zones of the Himalayas very nicely. Here the northernmost domain, Tethian sedimentary domain, and beyond that is the India-Sangpo Suture zone, and the central crystalline domain. They have the higher Himalayan crystalline domain. Most of the highest peaks are in this domain, and then the lesser Himalayan domain, low-grade metamorphic rocks, and the Shivalik Himalayan domain, fluvio-lacustrine sediments, sandstone, shale, etc., molassic sediments, they occur there. and beyond that, the Himalayan domain ends. We get the North Indian plains of Indo-Gangetic Brahmaputra plains. Now, distinctly enough, all these different domains of the Himalayas, they have their lithotectonic associations, which are distinctly different from one another. This aspect has to be remembered for dealing with the Himalayas in detail. On this representative vertical geological cross-section, after Rasul Sarkavi to 2010, we see the main STDS, or this is the Tethyan thrust. Earlier, we used to call Tethyan thrust. Nowadays, people tend to call it South Tibetan Detachment System, STDS. Then south of that is the MCT, south of that is the MBT, south of that is the MFT or HFT, main frontal thrust. All these important boundaries are not dipping. North is to our right, south is to our left, whereas the ITS is subvertical. So it is like a vertical subvertical wall. So this point is also to be remembered. Paleotectonic reconstruction of India has shown that, has proved that the Indian landmass has been moving northward, and associated with that was an anti-clockwise rotation. Eventually, that continent collided with the Eurasian continent, and that resulted in the vanishing of the Tethys Sea in between. That means the Tethyan ocean closed. All the sediments that were deposited in the Tethys Sea, they were folded, faulted, deformed, and then they became ultimately land. Okay, the Tethys Sea disappeared. Resolution of several nagging controversies. First, resolution of the controversy surrounding the Himalayan MCT, whether MCT is a discrete thrust plane or it consists of several thrust planes, discrete planar, or is it a shear zone, ductile shear zone, that kind of thing. So my study is mainly confined in the Garhwal Kumaon region, particularly the Alaknanda section between Joshimath and Gulabkoti via Helang, Poini village, etc. I studied that very closely, and the other 3 sections, Pinda river section, Goriganga river section through Munshiari, and Dharmaganga river section and through New Shobla region near Nepal border, those are also studied. But I found the Alaknanda section to be the most representative. The level of exposure, the quality of exposure, and the displaying of all the manifestations of deformation, metamorphism, etc., are very nicely studyable in that section. So I believe the resolution of the Himalayan MCT problem will be there. Resolution of the controversy on whether the higher Himalayan inverted metamorphism was caused due to thrusting along the MCT or not. Then the third, finding the cause of the higher Himalayan inverted metamorphism, finding the real nature of the STDS, that is the contact between the Tethyan Benin sedimentary sequence above and the higher Himalayan crystalline rock sequence below, finding the real geological status of the HHCU, higher Himalayan crystalline unit, whether extrusion tectonics or channel flow model is applicable to the higher Himalayan crystalline unit, finding the real geological status of the LHMU, that is lesser Himalayan metasedimentary unit, and finding the sequence of formation of the major thrusts or shear boundary zones of the Himalayas. This shows a map prepared by me of the Alaknanda section. River Alaknanda is coming from the Badrinath side, and then it takes a sharp turn, goes like that. Okay, and River Dhauliganga is meeting Alaknanda here. This place is called Vishnu Prayag. So this section was studied. There are very nice road section, main road section, and then close to the river there was another road section, and on the other side of the river there was a foot track section. So many of the findings of MCT zone, higher Himalayan crystallines, etc., they come from this region. Here I show the this blue area is the MCT zone, and this is the Joshimath area that I studied quite thoroughly. This is the Pinda River section. This is the Munshiari Goriganga River section. This is the Sobala, Khet, New Dharmaganga River section. In the Alaknanda section, the shear zone, MCT shear zone, has profuse shear sense indicators, all indicating typically top to south shearing within the MCT zone. The MCT zone in the Alaknanda section has been studied in good detail. I took the similar composition rocks like orthogneissic or quartzofelspathic gneissic rocks at different levels through the MCT zone and analyze their grain size. Here you see the appearance of the photomicrographs from which from north progressively towards south we see typical grain size reduction in the rocks. And these rocks, if this is the northern boundary of the MCT zone, Joshimath is to the northeast of us, and then these specimens are collected progressively along the main road. These are the specimen locations, and Helang is to the southwest. So these are they are indicating the influence, progressive intensification of shearing down the section within the MCT zone. Here, the grain size were measured, particularly matrix grains within the quartzofelspathic protomyelonite, myelonite, phyllonite, and typical gneissic rocks in the north, beyond the MCT zone in the crystallines. And they show a very typical, this is towards north and this is towards south. So southward, the grain size is decreasing. Here, the length of the matrix grains is shown. Here, the area of the matrix grain is shown. Here, the breadth or width of the matrix grains is shown. And here, in the last one on the here, we plotted the ratio of length and width. They are almost constant. So that means the grains which got reduced in grain size, both length and breadth in equal proportion got reduced. And this is an important feature. From the lower part of the MCT zone, we see the phyllonitization. That means recrystallization of myelonitic rocks. That is very prominently seen in the lower part of the MCT zone. And in those phylloниtes, we find myrmecitization of feldspar grains. These are some of the myrmecitization features in rocks. They are progressively reducing the grain size in an in situ manner. This is important. In situ grain size reduction. They are not having any effect on shearing, like lengthening in one direction or shortening in direction. This is very important to observe. In the later phase of MCT shearing, there are multi-episode shearing that took place. Maybe in the earlier part, there was displacement, but in the later part at least, to some extent, there was in situ grain size reduction. In the B diagram here, we see a rectangular feldspar grain, and that is showing grain size reduction progressively through myrmecitization. Here, in the bottom right, there are two things. On the right-hand side, we see the plane polar photograph. On the left-hand side, we see cross-polar photograph. If you look closely, following my cursor, there is a sigmoidal porphyroclast, and that is showing grain size reduction through myrmecitization. If we look at the cross-polar photograph, we see how nicely that grain size reduction through myrmecitization has progressed. And you see the matrix grains and the porphyroclastic grains are not distinguishable anymore. And after some further progression, probably we will not see the outline of the original water crust. So there is no volume decrease or volume increase during this stage of grain size reduction in the shearing. This is very important. So it may have a very important implication about the MCT displacement. It may be that MCT sheet has not progressed much further south from the north, unlike the alpine thrusts. That possibility is raised by these features. Okay, now we move on to the MCT sheet folds. The prominent folds out of 3 or 4 episodes, the most prominent folds we see in the crystalline rocks are the F2 folds. Here, a lovely in situ exposure of that fold, almost a profile section of the fold is shown. North is to our right and south is to our left. Clearly, an overturned fold is seen. The normal limb is the upper limb here. On the northern part, the normal limb is occurring, while the slightly steeper and thinner or stretched southern limb is onto our left. And this is probably reflecting in, as Professor Gilbert Wilson very nicely highlighted through his important studies. Sometimes we find tectonic weathercocks. Large-scale deformations are reflected in small-scale features. So this mesoscale or exposure scale feature might represent a very nice example of a large-scale F2 overturned fold. That is, okay, my observations are pointing towards that. As we proceed, you will progressively understand that. Now, Joshimot area, in this map, we show the relation between the F2 axis and the main stretching lineation in the crystalline MCT sheet. And associated with that are the main foliations in the rocks. Joshimot there, Helang there. This greenish blue part is the MCT zone. The pinkish part is the crystallines. So crystallines, these blue, green, and the pink, they together form the MCT sheet. So what happens from the inner part of the crystalline sheet, as we go towards the MCT zone, the shear zone, we find a progressive parallelism between the F2 axis and the main stretching lineation. The main stretching lineation are the red ones. So their plunge amount and plunge direction can be seen. North is there indicated, scale is there indicated. So as we progressively enter into the MCT zone, we find progressive parallelism between the F2 axis and the main stretching lineation direction. This is interpreted by me as that the stretching was probably a late seen F2 or post F2. Okay, it cannot be other way around. As far as the distribution of the Barrovian index minerals, defining the inverted metamorphism in the basal part of the higher Himalayas, this is a representative section, schematic section, MCT lower boundary. It used to be called as Munshari thrust by Professor Bhaldia or earlier workers. Bhaikrita thrust is the upper boundary of the MCT zone. There, the typical Barrovian index minerals distribution is like this, particularly in the Joshimot Helang section. Garnet from the middle of the MCT zone, then staurolite, then kyanite, and further upward, silmanite. Here we see a very good relation with the metamorphic minerals and the stretching lineation and the F2 folds also in this slide. Here, if you notice, there are black arrows in front of which there are elongated garnet grains in Joshimot gneiss or higher Himalayan crystalline gneiss. So what we see there is a kind of elongation lineation in the typical gneissic exposures, gradually turning into stretching lineation as we enter into the ductile shear zone or MCT zone. So the garnets, the Barrovian index minerals, garnets, they are showing the stretching effect. Here in the middle photograph, you see a photomicrograph showing the stretched and pulled apart staurolite grains. So these are also affected by the stretching, MCT stretching. So what does that indicate? It indicates that the stretching was post-metamorphism. This high-grade metamorphism was earlier than the MCT stretching. Clear? So MCT stretching or MCT emplacement could not have played any role in development of these metamorphism, during which these Peruvian index minerals grew or formed. MCT stretching was later than the high-grade metamorphism. In the right-hand side, we see a microfold, F2 fold, and it is deforming along the axial trace. This is the axial trace. A kyanite grain is clearly folded, showing folding by the F2. Again, this is used by me as implying that the F2 folding was post-Peruvian metamorphism, during which this high-grade mineral formed. So in these three phenomena, high-grade metamorphism was the first thing, then came the folding, and then came the MCT thrusting. This is to be remembered. High-grade event was the earliest, then came F2 folding, then occurred the MCT shearing or MCT emplacement. Here on a satellite image, you can see Joshimath area. This is Alaknanda coming from the Badrinath side. Here the meeting point Vishnu Proyag between in confluence between the Dhauliganga river, which is coming from this side, and then going towards the Helang area. This is Dhauliganga river. Along the Dhauliganga river, if we go, we get a place called Malari. Malari is important because Malari exposes the boundary between the higher Himalayan crystallines and the Tethyan marine sedimentary rocks. I just show from Malari to a place called Lopthal. Lopthal is somewhere there. The red line here is the China-India border. It is hardly 6 kilometers to 7 kilometers away from that border. There is a place called Lopthal. So I got an opportunity to go from Malari to Lopthal just on foot and prepared a map. You cannot see the details from here. Just I will tell you that this is Malari area. This boundary is the boundary between the central crystalline rocks, which are occurring to the southwest or to the left of us, and this belt is entirely within the Tethyan realm. Okay, there in this exposure, we found evidence of ductile shearing in semi-brittle condition. Okay, so Tethyan thrust, we used to, during our student days, we used to hear a lot about the Tethyan thrust separating the higher Himalayan crystallines from the Tethyan sediments. Later on, the STDS, after Birchfield and et al.'s work in 1992, that became very common to geoscientists, Himalayan geoscientists, to refer to that boundary as STDS, which is nothing but a normal fault zone type of thing. Okay. Here I show the difference between the rocks between two domains. On our right is a typical gneissic rock of higher Himalayan crystallines. On the left is crinoidal limestone type of rock from the Tethyan realm. This slide is also very important. Here, from the basal part of from the basal region of the Tethyan realm near Malari, we get this conglomerate. The conglomerate shows clear examples of the crystalline rocks. On the left-hand side photograph, at the center itself, there is a very good example of a crystalline pebble here. What better example to imply that the basement to these sedimentary rocks in southern Tethys, in contact with the Indian landmass, was made up of these crystalline rocks, the central crystallines or higher Himalayan crystallines. So they acted as the basement as far as the southern coast of the Tethys Sea with the Indian landmass, in contact with the Indian landmass, as far as that is concerned. This shows a panoramic view of the Lopthal area. In my title slide also, this photograph has been used. And Lopthal area, if you get a chance to go there, at every step you will get fossil, belenite or ammonite or some other fossils of Mesozoic age, they are full of fossils, as if it was a killing field. Black shell is the dominant lithology there. It is turning into black slate. There are clear evidence of repeated freezing and thawing and associated mechanical weathering of the rocks, pencil cleavage, etc. They are very nicely seen in those. So now we move to evidence-based and logic-based comments on the STDS. In the southern realm of Tethys Sea, the Tethian marine sediments were originally deposited on the basement made up of the higher Himalayan crystallines across a prominent unconformity. Okay, those conglomeratic rocks, they indirectly indicate the occurrence of an unconformity. With progressive closing of the Tethys Sea, contractional deformation affected the Tethian sequence under the sea in an interesting manner, giving rise to intra-formational unconformities, faults, etc. In the Tethian realm, wherever I could go, I saw the existence of such faults. Intra-formational unconformities, intra-formational faults. There are various types of parallel folds or concentric fold features, accommodation problems shown by those folds, very common. So they represent folding in a shallow level. These foldings might have started when they were in soft condition under the sea as a result of folding of different intensities, wavelengths, and amplitudes in different successive packets. So the earlier deposited ones started to show folding due to progressive closing of the Tethys, and the newer depositions above that were not showing any such folding. So repeatedly, this type of thing happened, showing different intensity of folding and deformation, thrusting, faulting, etc., at different levels within the Tethian sediments. Later, the same contractional deformation would cause major unconformity-guided southward thrusting along the so-called Tethian thrust of the Tethian rock sequence over the crystallines. With plate collision and closure of the Tethys Sea, the deformed Tethian sequence become part of the Indian continental landmass. The Tethian thrust brought the deformed Tethian rocks to such great heights, present height where the Tethian boundary, crystalline boundary, they are found near the top peaks, near the topmost part of the peaks, hardly 1 kilometer, 1.5 kilometer below the top part. Go to Mount Nanda Devi, go to Everest. So there, that boundary is occurring. So Tethian thrust brought the deformed Tethian rocks to such great heights above the crystallines that gravitational instability in the former rock mass had set in. Later, contraction and vibrational shocks, whatever, simultaneously with ductile shearing along the MCT zone in the deeper parts, in the ductile parts, played a triggering role to cause gravity collapse of the Tethian rock mass above through northward normal faulting, that is STTS. So the people or workers or scientists who found normal faulting, they might have found very clear example. But what is the story, entire story behind it? So the STDS shows an inverse reactivation along the pre-existing unconformity-bound Tethian thrust. Thus, a prominent unconformity turned brittle ductile thrust or shear zone, turned gravity collapse, reactivation of normal fault zone represent the whole story behind the STDS. The newly revealed aspects of Himalayan tectonic geodynamic evolution. Okay, the effects of post-collisional northward migration of the Indian plate getting blocked at the north wall of the ITS. That is another important feature. Division of the Himalayan orogeny can be done in two distinct stages. Birth of the Himalayas through continent-continent collision and post-birth growth of the mountain belt through continued post-collisional northward convergence of the Indian plate. And its blocking at the north wall of the ITS. Now, one question would help us understand that. When will the Himalayas stop growing vertically as well as southward? The obvious answer is the stopping of the northward migration of the Indian plate. If it stops, it will not grow anymore, Himalayas. Now, in a schematic model, I wanted to show these two birth and growth stages. In the top part, north is to our left and south is to our right. The northward moving Indian plate, the relatively fixed and rigid Eurasian plate, the north wall of the ITS is the blocking wall-like feature. So as we find the Indian plate after the closing of the Tethys Sea, the Indian plate that becomes part of the Indian plate. So the continent-continent collision started inducing perturbations, and these perturbations are nothing but the birth of the Himalayas. They are implying the birth of the Himalayas. Assuming there appears some easy assumptions which are not irrational. Assuming there was no aerial heterogeneity in lithology and rheology. For the sake of simplicity, no thrust or fault is shown here. Now, in the post-birth growth and development stage, what we see continued northward migration of the Indian plate, and there is continued south-directed active push. This is the active force causing the deformation in the Himalayan zone. They are causing further deformation within the frontal part, closer to the ITS, that part of the Indian plate. And as India will continue to move, these deformation zone will continue to move southward, widening the Himalayan belt progressively. And within this deformation, there are clearly examples of distinct folding episodes followed by short phases of thrusting episode. Okay, so when the folding is not able to accommodate the strain any further, thrusting occurs at the front, and then newer part of the Indian plate start getting affected by the this deformation mechanism. So post-birth growth and development of the Himalayas due to continued migration of the Indian plate. In the next diagram, if we closely notice, throughout the Himalayan orogeny, there is a pervasive Himalayan shear domain. So here I explain that. Northward movement of the Indian lithospheric plate, the relatively fixed Eurasian rigid plate, this is the northern wall of the ITS. The active push is coming from there. So top side is exposed to open air. Okay, so there is no friction or cohesive resistance to the southward push, whereas on the bottom side, it is closed, confined. Lower part of the lithosphere or upper asthenosphere exerting cohesive resistance to the southward push. So there is an inhomogeneity in the push, and that is resulting in a shear domain, top to south shear domain, as long as the Himalayan origin is continuing. Top to south Himalayan shear domain active since plate collision, as the lithosphere has from top brittle, ductile, and ductile stratifications. In the top part, we find brittle zone, more compact type of thing. As we go downward, we find softish thing, ductile thing. So that is resulting in this broad overall Himalayan shear domain. Reasons why the Tethyan sediments show complex structures. Okay, as I was briefly explaining earlier, so this is a still wide Tethys Sea subducting Indian lithosphere, sedimentary layers at the bottom in the Tethys Sea. So they are horizontal, but and the profound unconformity, first stage, which would later turn into STDS. This is a profound unconformity between the Tethyan sediments and the basement, crystalline basement of the Indian plate. Now narrowing Tethys Sea. So what happens to the bottom sediments which were deposited earlier? They start getting folded. They start getting faulted, more deformed. Whereas in the top part, in the top packet of sediments, they are still undisturbed. So this type of thing is happening. Okay, and as a result of the narrowing, progressive narrowing, and progressive northward movement of the Indian plate, those deformed Tethyan sediments or sedimentary packets, they start moving northward through Tethyan thrust, through other interformational thrust like that. And due to that pressure, incipient F2 folds in the crystalline rocks also develop. Interformational unconformity turning into thrust fold. These type of things are going. Now, very briefly, the requirement of confirmatory geophysical investigations in the Himalayas. The newly revealed aspects of Himalayan tectonic geodynamic evolution are expected to be substantiated also by geophysical observations. Thanks to the geoscientific data collection from the Himalayas for almost the last 2 centuries and putting the crucial observations in correct perspective with sound geological reasoning, the big picture of the tectonic geodynamic evolution of the Himalayas is now pretty clear. An emphasis is required now for geophysical authentication. Only 3 to 5 well-chosen transects will do, particularly some along the existing balanced cross-section lines. The famous Snorkel transect of Canada may be used as a model. Just a brief mention of the Snorkel transect of Canada. This is the straight line transect. In reality, there was some curvatures or line segments of different lines. This is the mean line, and the results of that geophysical investigations, they are shown. And this is from Global Tectonics book by the Chiari, Kevis, and Vine. Okay, the geological investigations or findings, the geophysical findings, everything, they are nicely bringing out what happened. And a fossil subduction zone is identified or discovered from there. That is excellent. And finally, the conclusions. My conclusions are, big picture of the Himalayan orogenic evolution is not as complex as many would believe. India-Eurasia collision gave birth to the mountain belt, but its post-birth growth and development have been depending on the continued post-collisional northward migration of the Indian plate getting blocked by the Eurasian plate. Such blocking generates a rebound southward push from the northern wall of ITS that progressively folds and fractures, that is, deforms the Indian lithospheric layers, thereby giving rise to the southward expanding Himalayas, north dipping thrust progressively developing one after the other from the hinterland to a foreland sequence. Localization and development of the major thrusts, that is tectonic discontinuity zones, were influenced originally by the existence of aerial heterogeneities in lithology and rheology. Pre-existing major unconformities played a big role in such localizations. Of the 4 major tectonic discontinuities, namely STDS, MCT, MBT, and MFT, only the STDS clearly shows signatures of tectonic inversion, not the other ones. However, STDS is a misnomer for the HHCU, Higher Himalayan Crystalline Unit, and Tethyan Marine Sedimentary Unit contact, as the term only refers to the 3rd or final stage, ignoring the 2 earlier stages of a distinct 3-stage evolutionary history of that contact. First was unconformity, second was brittle ductile top to south thrust shear, Tethyan thrust, third was inversely reactivated gravity collapse normal fault zone, and that is why a good name or a new name like main inverse tectonic zone would be better than the STDS for this contact. Of the said 4 major discontinuities, we find first developed Tethyan thrust, that is a precursor of STDS, then MCT, then MBT, and then MFT in a distinct hinterland to foreland sequence. Okay, broadly simultaneously with the MCT emplacement at deeper level, the STDS gravity collapse normal faulting as inverse reactivation took place at higher crustal level. So that phenomenon, normal faulting, gravity collapse normal faulting, was a later phenomenon than the Tethyan thrust event. That has to be understood. The broad similarity in age between the MCT thrusting or shearing and STDS normal faulting implies a simple gravity-induced cause and effect relation. MCT shearing below triggered this gravity collapse normal faulting at the top due to an already developed gravitational instability. That means ground surface slope nearing or equaling the permissible angle of repose or factor of safety, what we normally call in unstable slopes like landslides, etc. So that slope nearly approached that factor of safety, unstable condition. And then down below, there was MCT movement, and it probably triggered a kind of vibration or something like that, which caused that gravity collapse structure to develop. It would be erroneous to consider that the STDS operating in a shallow and brittle domain and the MCT operating in a deep and ductile domain showed an in tandem reverse mobility. MCT is showing movement top to south, whereas the STDS, as everyone believes, particularly those who coined the term and studied it in detail for the first time, they see that it is top to north. So one is top to south, the other is top to north, in tandem reverse mobility as an integral part of a unique tectonic phenomenon like extrusion tectonics or channel flow. That would be very erroneous, in my opinion. Okay, that cannot happen. Geologically, it's not feasible. The 3 crystalline rock sequence of the higher Himalayas has not witnessed extrusion tectonics or channel flow. The structural design observed from this crystalline domain and interpreted by some workers as due to extrusion or channel flow is in fact representing a large-scale overturned south vergent anti-formal or anticlinorial F2 fold geometry. The same large-scale south vergent overturned anti-formal or anticlinorial F2 folding caused folding of a pre-existing normal Barrovian isograd sequence. This is why we now see an inverted isograd sequence in the inverted southern limb of the fold, exposed at the base of the higher Himalayas. F2 folding postdated the prominent high-grade Barrovian metamorphism, as I explained and proved probably clearly earlier in this talk. MCT shearing had no role to play in the formation of the inverted metamorphic isograds because this shearing or stretching took place after the formation of the said isograd defining cogenetic Barrovian index minerals. MCT shearing was late seen F2 or post F2 in time and was confined mainly in the inverted limb of the large-scale F2 antiform or anticlinal. The successive southerly development of the Himalayan foldland basins like Dagsha Isipathu at Yosin time at north, then Sivalik, Mayopaisin further south, and the present-day Indo-Gangetic Brahmaputra alluvial plain basin recent at south clearly indicate progressive southward widening of the Himalayas. Seismic reflection profiling along 3 to 5 well-chosen transects, a few coinciding with the available balanced cross-section lines. Professor Gautam Mitra, Dr. Kathakuli Bhattacharya, they have worked, and others also, balanced cross-section lines across the Himalayas. Taking the snorkel transect of Canada as an appropriate example is the demand of the time now. I dedicate this oral presentation to the memory of 3 doyens of geology, Professors K.S. Bhaldia, John G. Ramsey, and Peter Molnar, who are no more with us, but through their pioneering contributions, who gave us excellent vantage points to look further. I acknowledge, I express my deep gratitude to my teachers who taught me to observe and think independently, keeping in mind the laws of nature, particularly Professor A.K. Saha and Professor Dhruva Mukhopadhyay at my basic level of understanding geology. Then Professor M.R.W. Johnson, Michael Raymond Walter Johnson of Edinburgh University, who introduced me to the intricacies of Himalayan geology, and later my research guides, Professor Taposh Bhattacharya and Dr. Subhajit Sinha. I am also deeply indebted to so many geologists across the world. Professor Mike Searle of Oxford University is one among them, who openly discussed with me on various aspects of Himalayan geology, and also to the PG dissertation students and the groups of undergraduate students who accompanied me to the difficult Himalayan terrains for fieldwork. I am very thankful to my wife Sushmita for her constant support in my scientific pursuit. Thank you all. I finish here, and I would be very happy if that's all.
Thank you very much, Subrata. Let's now open the floor for question and answer. If you, I think there is one raised hand already. Sir, please go ahead. Neptune, sir.
Yes, Professor Ghosh, that was a wonderful talk. And especially, I really appreciate your talk because it has so much actual granular level field data, which is missing from many of the new papers, which makes grandiose hypothesis without, actual grounded in actual field data. I was just curious. You mentioned that the major folding, which seem to be related to the thrusting, is the F2 folds in the central crystallines, and the metamorphism is pre-folding. I was wondering what is the nature of the F1 fold and what caused the major metamorphism in the Himalayan in your scenario, in your model?
Okay, Nityunda, thank you for the question. In reference, in the context of my talk, I cannot delve into that in detail. Okay, I focused mainly on F2. Now, as far as my, whatever observations I have made, it appeared to me that F1 folds are more like, as common in many other places, interfolial type or some kind of very tight to isoclinal folds like that. And they are, in comparison to the F2 folds, much smaller in scale. F2 folds, if you read my abstract for this talk, they are explained in greater detail. They are multi-scale, multi-order folding. You can see from microscopic scale folds to almost post-mesoscopic or megascopic scale, like the anticlinorium I am talking about, affecting the entire higher Himalayan crystallines. They can only be mapped probably. You can see the evidence of their limbs on maps and likewise. So that is one part of the question. And the other folds, post F2 folds in the MCTC, they are mainly localized folds, F3, which developed during the MCTCI, and F4 also. As far as if we just strictly say about the time of formation of those folds, then F4, of course, came later than the F3. But F3 and F4 are seen MCT or post-seen MCT, seen shearing folds. That is one thing. About the high-grade metamorphism timing, my observations cannot pinpoint. Okay, but they are pre-F2 without doubt. Whether they are pre-Himalayan, I cannot surely say, but I would tend to believe that they are probably pre-Himalayan. Whether they took place during the Himalayan orogeny or they were earlier than Himalayan orogeny, then my vote will be probably they were earlier than Himalayan origin. But it is my surmise. I did not get any clear-cut proof yet. Is that all right? You think?
Okay, thank you.
Any further questions? Please raise your hand and ask.
Yeah, I would also,
yes, sir. Please go ahead.
I would also appreciate if you have any questions or suggestions, because I want to formulate these in proper paper or maybe for my thesis. So I seek ideas also, constructive ideas, if there is any.
Yes, sir. Go ahead. I think, Dhruvo, sir, you are muted.
Can you hear me now?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Yeah, okay. Subrata,
Sir.
What intrigues me is that you have discussed about the sequence of the formations of structures mostly observed on mesoscopic and microscopic scale.
Okay.
And now there is the biggest picture of the deformation of the movement of the Indian plate below the Tibetan and Eurasian plate. And this correlation between the sequence of structures found on this mesoscale and the picture of the continuing subduction of the Indian plate, this is what intrigues me, that what caused these different phases while the Indian plate is continuously going down below the Tibetan plate.
Okay. May I start, sir?
Yes.
Okay. Now, I thought about that also, where I discussed the pervasive Himalayan shear domain during the Himalayan origin. Throughout the Himalayan origin, this type of dynamic shear domain is continuing. Now, if we focus in the lower part, when the collision took place, this is a classic example, which is not present probably at many places in the world, where in many places I would guess that the plate, as soon as the plate collision takes place, the plate movement stops. Plate movements stop. This is not the case with the India-Eurasia collision. Now, what happens when there is an impact like this collision? What happens? There is always an effort of the rock mass to readjust itself with the new scenario. And what is that readjustment? One is, as we distinguish the brittle domain in the top part of the crust, the ductile domain and transitional domain before that, and then the ductile domain, that kind of readjustment to take place. Now, with that readjustment, what happens as the northward movement of the Indian plate is continuing, there is a great likelihood. I did not mention about that because that would enlarge the scope of the talk so much that I would guess, I did not read thoroughly about the points that you mentioned, but I guessed that this is a zone, continental collision zone, where subduction again started after the collision, after some readjustment after the collision. So the lower part has again started to move below the Tibetan part, and that's why in this part, below the Himalayas.
What is the reason for your assuming this time difference?
Which time difference you are
between the collision and the renewed subduction?
Time difference for anything like we see, whatever we see, the impact, they are a very quick thing. But in case of this type of thing, it's a geological thing involving so thick a plate. So there is obviously some time difference, time lag.
Why can't you think about a continuous process?
Continuous process, that impact, that blocking is there. So that has to be properly accommodated by the impacted block of the lithosphere. And after that shock is absorbed properly, then due to the push from behind the northward moving Indian plate, that is continuing to move, continuously moving as we go south to Kanpur, to central India. So that push will start the subduction again. So that was to get readjusted in the new scenario. That time was consumed. That is what I feel. Is that reasonable, sir?
Okay.
Thank you, sir. And if you want to ask your question, please. I think Ayan has written the question in the chat box, Subrata, if you want to look at it.
Okay, let me see. Could you read it out, Jyotirmoy? That would be very helpful for me, because I want to remain here. If I want to take help of any slide, I can go easily to that, to reply to that question.
Okay, so he wants to ask what ask what to you are the problems considering a return flow or extrusion tectonics. A downward tapering wedge would cause high dynamic pressure in the lower part that would give rise to a pressure induced flow, a combination of voiceless flow and Couette flow, simple shear. What kind of flow wedge can also explain the normal fault movement on STDS?
Okay, Oyan Patsha, I know he was our undergraduate student at Jadavpur Government College. And thank you, Oyan, for your query. Now, what I think about, you must realize that my observations do not support the existence of extrusion tectonics or the channel flow model. Okay, because what I think, if I tell that, you probably would get the answer. I'm not going into the intricacies of the specifics of the model, but what happens, it involves a huge mountain belt. If you consider the length of the Himalayas, it's very huge. Now, the channel flow or extrusion tectonics in a vertical sequence. So how can it be so orderly throughout the length of the Himalayas? That is one big question. Second, such channel flow would require huge amount of energy to get executed for an entire mountain belt like the Himalayas. Now, if we consider the tips, the ends of the Himalaya belt, there such flow is not seen so much. So why in the middle part of the last part, first part of the Himalayan belt, there is a huge source of energy, whereas at the end there is sudden disappearance of that energy source. That kind of practical non-feasibility appears. Okay, and let me explain a bit further. In a vertical sequence, we can see examples of extrusion. If you have seen any overripe mango, if you kick it, particularly if you at one side, if you cut it a little bit, and then if you kick it from above, the seed will show extrusion tectonics type of thing. Now, there is a huge pressure externally given, and that's why this extrusion of that seed of the overripe mango is taking place. Similar example can be seen in truck below, if it is going off route, a truck, and if there are rock blocks, small rock blocks like those which are seen in the railroad ballasts, that size of rock is there on the road. Sometimes you see extrusion type of movement of those blocks from below the truck tires when the truck is moving. Okay, and that is extrusion. There again, huge amount of external pressure, vertical load is generated externally, which is causing that extrusion type of thing. Okay, moving away from that original.
Sir, what I am trying to say is that you are considering a rectangular block, but if we think it is a kind of accretionary wedge with a triangular shape, the Himalaya, and there is Tibet in the overriding plate, like the similar in the tectonic diagram, we see an accretionary wedge. In that kind of situation, because the accretionary wedge is tapered in the bottom, and the subducting plate is taking the sediments and the material towards the corner. So because of that flow constriction, there will be a huge high dynamic pressure in that corner. And that dynamic pressure, and because the upper surface is stress-free, that dynamic pressure can give rise to a flow, upward flow. And even in that model, it shows the velocity will be highest in the central part, as you have correctly mentioned. So in that case, what are the problems? Because in a rectangular block, yes, you are correct that there is it is quite hard to create such a pressure or energy. But if the motion is like if the acceleration is a tapering channel, then because of the corner or because of the constriction in that corner, that can give rise to a high dynamic pressure. That was my
Okay, the extrusion tectonics mainly refers to, or channel flow mainly refers to the higher Himalayan crystalline rock sequence. Okay, in that part, that is showing the extrusion tectonics. Okay, the overburden is the Tethyan marine sediments, and below that the lesser Himalayan rocks are there. So in between those two boundaries, MCT below and STDS above, within that the crystalline rocks are showing extrusion tectonics. They are going northward and upward slightly. Okay, that is the extrusion tectonics channel flow. What I find is geologically it's not feasible very much. Rather than that, the same things that geological evidences, the occurrence of the metamorphic minerals, that can be explained more beautifully and elegantly by simple overturned fold model or anticlinorial fold model. South Virgin, large-scale antiform. And because the Himalayas is so vast, we must not, like in the Malari belt I am talking about, we did not see much of the normal faulting effects. And that is quite possible. There are three different stages in that boundary. So depending on the geological variations laterally, some phase would be more prominently reflected at some areas, and the other phase would be more prominently reflected. That is quite possible. So I was not very bothered about that. But my observation is that the STDS took place in a distinct tectonic environment, and which was in no way connected organically to the MCT. But extrusion model and channel flow model, they consider these two boundaries as integral part of that scheme of deformation. That is where I beg to differ. The one is taking place in below very shallow level, the other at much greater depth at ductile level. So those two cannot be put together to explain a particular tectonic model, comprehensive tectonic model like that. That is my essence. Okay.
Thank you so much.
Okay, we can talk later when we meet. If that would be very nice.
Okay, Neptune sir, you had another question, it seems.
I'm sorry.
No problem.
No, please go ahead.
Most welcome.
I think Professor Ghosh's work, one thing that his work actually highlighted is the Himalayan metamorphism, the major metamorphism and the deformation that we see, especially in MCT and other places. These two are not connected. And the metamorphism possibly predates that deformation. And the entire model of orogenesis, where metamorphism and deformation go hand in hand, there's some disconnect between there. Some of the data that Professor Ghosh might look at, there's lots of geochronological data already existing. For example, I think Cottle and others, they have worked, you'll find details in Goscombe's paper also, is from within the garnet, they have dated the monazite, and they're at the core of the garnet. So they do date the time of growth of the garnet. The oldest date they have gotten about 38, 40 million years at most, which postdates the collision by about 10 million years. And the second thing is, if you look at the Himalayan granites, which are about Miocene, so that might be the upper limit of metamorphosis in the Himalayas. So how his model fits with these kind of geochronological constraints, that's something to be looked into. As far as channel flow model, or the critical taper model for thrust zone development as such, and which has been applied to Himalayas also, the major problem with critical taper model is you consider the entire mountain belt or the whole Himalayas as a big pile of sand, which is being pushed by a bulldozer. Mm-hmm. This model came from structural geologists who look at the seismic data oil company geologists who looked at seismic data from passive margins, where you have passive margin sediments, which are pretty homogeneous and water saturated, so easy to deform also. But the same thing, if you really cannot apply the same model to an old mountain belt like the Himalayas. I mean, look at Jonthar quartzites. You have a 400 kilometers or 15 kilometer thick quartzite. I mean, can you really, and you have shale on the other side. Can you consider that as a pile of grain of sand where they're free to move between the grains? So critical taper model also is finding difficulty in other mountain belts too. And the same thing with the channel flow. With the channel flow, the channel flow, the metamorphism, cooling, and emplacement has to take place after the Himalaya has risen, after the exhumation and uplift of the Himalayas, which is Miocene or younger. And you are getting dates much older than that. So channel flow really cannot, I mean, neither of these two can explain the tectonics of the Himalayas. So what's needed, especially from an august group like yours, who are structural geology tectonics people working right at the place, is find a new model for development, not only of the Himalayas. Whatever is true for the Himalayas will be true for orogenesis all over the world. That will be a big contribution to the geology. Thank you.
Thanks a lot, Neptunda. And we'll
Thank you
discuss
very
some
much.
more.
Any other question, if anyone has? Okay, if not, then I would really like to thank Professor Ghosh for delivering this talk. And it was really an insightful talk, and I hope especially the students actually take some lesson from this. And it was really nice and very insightful. So with that note, I would send the next invite for next month's seminar pretty soon. And thank you for all. Thank you to all for joining tonight.
Thanks
Bye.
a lot, everyone. Thank you. Thank you.
Bye. Bye.
Thank you very much. Thank you. See you then. Thank you.
So good to see you all, sir. Dhruva Babu ke namaskar janachi. I don't know whether Tapos is there or not. I can see